Multivariable calculus, we're looking at the first day of 14.6. We're going to take derivatives, but a little bit differently. You can see our learning target at the top of the page here. I can find directional derivatives. Let's read this together. Earlier in this chapter, we learned about partial derivatives, and it was with respect to x and with respect to y. Really what we were seeing is that these derivatives represented tangent line slopes, which of course are instantaneous rates of change, where tangent lines were drawn to trace curves determined by vertical planes, where either x was held constant, like x equals 5 or x equals -3. Y would equal a constant as well. You could draw two different vertical planes that would intersect your surface at a curve. We could then find a tangent line much the way that we had done before. In other words, this would be an instantaneous rate of change in the direction of x or in the direction of y, depending on which variable that we were holding constant. But today we study directional derivatives. These are slopes of tangent lines drawn to a point in the direction of a unit vector u. You can see this is depicted here. Highlighting in yellow, we've got a unit vector u. You could envision that we create a plane, and here's this vertical plane, and it would cross over and touch and form a curve on that surface. We could create a tangent line there. So that's really what we're doing today. We're going to find rates of changes in any direction, not just in the x or y direction. And that can be so incredibly helpful down the road. Here's a theorem that should be memorized. If f is a differentiable function of x and y, then f has a directional derivative in the direction of a unit vector u with components of a for x and b for y. D sub u, notice we're not writing d sub x or d sub y here, we're writing d sub u. Plugging in a starting point, x naught, y naught, is going to be, look at this, the partial derivative of f with respect to x, substituting in that initial point, multiplied by the x component. So we have our x derivative multiplied by our x unit vector component, plus here's our y derivative, f sub y, partial derivative of f with respect to y, plugging in our initial point, multiplied by the y component of our unit vector. Now, of course, as you begin to envision a unit vector, please do understand that a unit vector, if we were to, draw that as, a comma b, we'd be going a to the right and b over if this was on a xy plane. Remember, a unit vector has a length of 1. So the angle that's made with the x-axis, theta, really can help us out quite a bit. You can say, well, you remember we've talked about this so much. X equals r cosine of theta and y equals r sine of theta. If you wanted to find this x distance and this y distance right here, you could say, well, a would have to be 1, which is that r length, times the cosine of theta. With y here, you could say, well, y, your vertical step here is b. B is equal to 1 times the sine of theta. So what are we getting at? We can compare what we had right up in here, which is very true, and you should have that memorized. But you could say, well, if a is really the cosine of theta, and if b is really the sine of theta, we'd be able to have this alternate form, which is even very often a lot more convenient. So let's jump in and see a problem that we can tackle together. We're going to find a directional derivative of f of x, and f is given to us right here. U is the unit vector in the direction of pi over 6 radians. So this is just part A. We want just a general directional derivative. We're not even plugging in a particular point. So, for part A, let's find our derivative with respect to x. When we do that, I hope you'd quickly agree it's 3x squared minus 3y. And of course, the derivative of 4y squared is just going to be 0. The derivative with respect to y, well, the x cubed is a constant. It goes away. Negative 3xy with respect to y is negative 3x. And then we'd have plus 8y. Well, if we were to look right up in here, we could see that, our unit vectors in the direction of pi over 6. So I could say d sub u of f of x comma y is going to be f sub x, which is 3x squared minus 3y, times the cosine of our angle. Well, that's pi over 6, plus, then we could say, well, what's coming up next? Well, our derivative with respect to y, that's negative 3x plus 8y. And then we're going to multiply that by the sine of our angle. That's the sine of pi over 6. We know that the cosine of pi over 6 is actually a half. Pardon me, shame on me. The cosine of pi over 6, we all know, is radical 3 over 2. My goodness. The sine of pi over 6, that's what I had meant to say, is going to be 1/2. So we have that much right here. And, we could even leave this right here as a final answer. Whether you wanted to distribute that in is totally up to you. But at the end of the day, let's do part B right here. We can say d sub u would be f of 1 comma 2. What does that mean? Everywhere where we had our x, it's really like an x naught. We're going to plug in a 1. So they have 3 times 1 squared minus our y is a 2. That's 3 times 2. Here's our root 3 over 2. And then we'll say negative 3 times our x, which is negative 3 times 1. Plus 8 times 2, and here we've got a 1/2. So let's just clean this up real quick. Inside, here's 3 times 1, that's just a 3. 3 times 2 is 6, so 3 minus 6, you get negative 3. So that's negative 3 times root 3 over 2. Inside here, you've got negative 3 plus 16. Well, negative 3 plus 16 is 13, and then we could have 13 all over 2. Well, getting a common denominator is pretty easy because we have a common denominator of 2. This is a rate of change. It describes how the function is changing, really those z values, how they're changing as we're moving in the direction of a unit vector that makes pi over 6 radians, 30 degrees, with the x-axis. Okay, so, just really a little bit different from things that we've been doing. But I hope you can see it's very much related, very close. You're going to see this symbol so much. That upside down triangle is called the gradient. The gradient of f is actually a vector function. You could call it a vector operation. It's going to turn your function into a vector. The x component is going to be the partial derivative with respect to x. The y component is going to be the partial derivative of f with respect to y. And you could write that in this bracket notation or in terms of vectors I and j. But let's go ahead and take a real quick look at what the gradient is going to be. Over and again, I think you're going to see that we're going to be taking derivatives. The derivative of sine of x with respect to x, that's going to be the cosine of x. The derivative of e to the xy with respect to x, well, we need the chain rule. We're going to have e to the xy, but the derivative of that argument with respect to x, it's just going to be a y, so out comes a y. F sub y, the derivative of f with respect to y, derivative of sine of x goes away, doesn't it? And you'll have e to the xy, but this time when we take the derivative of xy with respect to y, out comes an x. So for part A, when they say, would you find the gradient of that function. It's going to be a vector. It's a vector function at that. The x component is the cosine of x plus y e to the xy, and the y component is x e to the xy. But then for part B, they're going to say, well, that's all lovely, but let's plug in 2 comma 0. That means wherever we see an x, plug in a 2. Wherever we have a y, plug in a 0. Well, that's going to actually make that first component work out rather quickly. I think you can see what's happening. The 0 times that e is going to go away. Cosine of 2 radians. Well, we can have that. You don't need to have pi in your radian form, of course. E to the 0 is 1. 1 times 2 is simply a 2. And this, guys, is your gradient applied at the point 2 comma 0 when x is 2 and y is 0. Well, here's something that we can link in. The gradient compared to our directional derivative. D sub u f of x comma y, we did that earlier on the front page. And remember, we said like a unit vector u might have had components of a comma b. And you might think, well, my gosh, is the directional derivative really equal to the gradient, which is a vector, dot product with a dot product to the unit vector? Let's see it in action. Here's a proof. It's a very short proof. It's actually delightfully short. Look, you'll have your x component is f sub x for the gradient, f sub y for the gradient's y component. We're going to have a dot product of a comma b. And you know how the dot product works. X component times x component plus y component times y component. What are we seeing? If we went right back to the beginning of our notes, right here with what we were memorizing, that's right here, f sub x times a plus f sub y times b. Wow, it's the gradient of your function dot producted with the unit vector's components. Wow, you do that and you will find your directional derivative. Let's see if we can squeeze this last example in for the video. I think we can. Find the directional derivative here. Not surprisingly, it's probably a good practice to just take partial derivatives with x and y. X squared y cubed, you'd get 2x y to the third. Derivative of negative 4y, that just vanishes. F sub y, you're going to bring down a 3. You get 3x squared and then y to the second. But the derivative of negative 4y with respect to y is actually negative 4. Now, of course, we're going to apply this directional derivative at the point 2 comma negative 1. But we're doing that in the direction of v. V is this vector of 2 comma 5. And let's take a look at the length of v. Sadly, I think you're going to see it's not a unit vector. That's 2 squared plus 5 squared. That's 4 plus 25. It only takes you a moment to see that this length is radical 29. So we need a unit vector. We're going to take these components of 2 and 5 and we're going to divide them by that length. When you're dividing by the length of radical 29, your new length is 1. So if we were to come up here and just do a quick directional derivative, following what we're seeing at the top of the page, we'd need a dot product dotted with u. End result, we're going to say it's f sub x times a plus f sub y times b. You could think of it as the dot product also, of course. But here's your 2xy cubed. Your a is 2 over radical 29. F sub y is 3x squared. Y squared minus